So let's do one more example. We again want to express a vector as a linear combination of other vectors. This time we want to express it as a linear combination of three other vectors, if possible. Okay, so what does that mean? That means that some constant times my first vector plus some constant times my second vector plus some constant times my third vector will equal vector 3, 1, 1. Okay? So if we could find the scalars a1, a2, and a3, we'll have our answer, right? We just plug them in for our final answer. So to do this, we need to solve a system of linear equations. This is an equivalent way to express a system of linear equations. So I could write this as 1a1 plus 2a2 plus a3 equals 3. That would be my first equation from the first row. Second equation from the second row, I'd get 3a1 plus a2 minus 2a3 equals 1. And the last row, I'd have negative 2a1 plus no a2 plus 2a3 equals 1. Okay, these two ways of expressing this are equivalent. They mean the same thing. We're asking the same thing. Okay, and because we're asking it, it's helpful if we could start thinking about this in the same way. And so we know in order to solve this, just like the system of linear equations, we can represent it as an augmented matrix, where the columns of the matrix are the vectors in our linear combination expression, and the augmented part is the vector we want the linear combination to equal. Okay? So we could jump straight from here to here. All right. So if we want to solve this system, we can rewrite this. We could use elementary row operations to transform this into a reduced row echelon matrix. And again, let's let the computer do it for us. So you can see my result from the last example still in there. Let me just add a new cell. We don't have to get rid of that. I could continue from this point. So I want a matrix. My matrix, the first row is 1, 2, 1, 3. Next row is 3, 1, negative 2, 1. And the last row is 2, 0. I'm sorry, that's a negative 2, isn't it? Let me squish this down a little bit just so we could really see that. Negative 2, 0, 2, 1. Okay, and I've mentioned this before, but the augmented line there, it's really there for our benefit, just so we know which side different elements are on. We know that on the other side of that vertical line, the augmented part of the matrix, that's on the other side of the equal sign in the equation. But mathematically, we're doing the same operations to the matrix whether we have that augmented line or not, which is why we don't need to represent it in the computer. Okay, we just write the whole row, and we just have to remember that we have an augmented part to the matrix. Okay, whoops. Okay, now I want to find the reduced row echelon form of matrix B. So B dot RREF. That gives me the reduced row echelon form of matrix B, and let's make it so it prints it nice and pretty, makes it easy to read. Okay, and so here, just maybe blow that up a little bit. So here is our matrix. The reduced row echelon form of our matrix. I'll just move it over here and I'll copy it down. And so I get 1, 0, negative 1, 0, 0, 1, 1, 0, and 0, 0, 0, 1, where the last column is the augmented part. Okay? Well, if you're paying attention and you've remember what we've learned in the past few sections, we may notice there's an issue here. Notice the last line. We have 0, 0, 0 all in the coefficient matrix and a 1 in the augmented part. So this line translates to the equation 0 equals 1. And that's a nonsense equation. That doesn't make any sense, which means that this system of equations has no solution. Well, what does that mean in the context of linear combinations? It means there is no choice for A1, A2, and A3. There's no values that we can pick so that we can write these vectors as a linear combination. We could write 3, 1, 1 as a linear combination of these other three vectors. Okay? It's not possible. It is impossible to express 3, 1, 1 as a linear combination of the other vectors.